we'll wait a few minutes to see if anyone joins and then we'll start. Right, so I'll start now by sharing my screen. Welcome to the fifth live session of the course Structural Biology. This is the last class that we will be talking about X-ray crystallography, and we'll go into some final details of the X-ray crystallography process. So just to recap what we learned in the previous class, we can't visualize molecules directly using X-ray. This is because a single molecule is a very weak scatterer of X-ray. So most of the X-rays will pass through the molecule without being diffracted. And even the X-ray that is diffracted has so little intensity that the diffraction spots are too weak to be detected. So the solution to this is that instead of using X-ray crystallography on a single molecule, the X-rays are passed through crystals. Crystals, as you know, are made up of three-dimensional repeats of ordered molecules. And the X-ray diffraction waves from each of these molecules reinforce each other through constructive interference. So the resultant diffractive beam has high intensity and is strong enough to be detected because the intensity of each of the intensity from each of the atoms in the crystal are reinforcing each other and becoming of intensity strong enough to be detected. So there is something called Darwin's formula, which says that the diffraction intensity is proportional to the number of unit cells in the crystal. So as you know, a crystal has many unit cells, which is the repeating unit of the crystal. And in the unit cell, there can be many molecules. Threshold, the Darwin's formula says that in 100 millimeter cube crystals, there are 10 to the power 12 unit cells. And that is why when, suppose this is the crystal, so in the crystal, there are ordered periodic arrangement of molecules. 1 second, someone wants to join. I'll just admit them. Right, I'll continue. Please admit anyone else if they want to join. So I was just recapping the previous class. So where I was saying that a single molecule is not enough to visualize X-rays. So when there is a crystal, there is an ordered periodic arrangement of molecules. And so each of the diffracted X-ray beams have constructive interference, and the overall amplitude of the final diffracted beam increases. That is, the intensity increases. And so from a crystal, the X-ray diffraction pattern is clear enough. Whereas from a single molecule, it is very weak. So diffraction, you have seen generalized diffraction patterns in previous classes. So these are generally read on image plates that are circular. And after, suppose like you have mounted the crystal on the goniometer at a specific angle, and you get the diffraction pattern at a specific angle. After that, the diffraction pattern is erased with a fluorescent light, and then you change the goniometer angle and you get the diffraction pattern for another angle. Like this, you get the image of the crystal from different angles, and you put all the data together to get the final 3D structure of the crystal. So often what you will see is, since that the detector is square, the corners of the diffraction pattern have higher resolution. And if you zoom in enough, the intensity values of each of the spots can be found. So the intensity values like this are, for each of the spots, the intensity values will be given. And you will see that in the diffraction pattern, there are certain red spots. The red spots indicate that there is some overload. So basically, in each of these spots, you will see a Gaussian distribution of intensity. So in the middle of the spot, the intensity will be maximum and it will decrease on either side. In case of the red spots, what happens is that the intensity crosses the threshold limit that the detector can detect. And that is why the red spots are kind of errors, because you don't have the intensity peak recorded because it is exceeding the limit of the detector. And so you cannot accurately determine the intensity of these red spots. Then you have learned indexing, Miller indices, in the previous lecture. And basically, there is a program which, after you get the diffraction pattern, the program will run and find out that which is the best lattice group to which the diffraction pattern matches. So you had learned about the 14 Bravais lattices in the previous class. So the program will calculate the deviation from each of the lattice groups. So this is the result for the diffraction pattern shown in the previous slide. So that diffraction pattern has perfect match with a primitive triclinic Bravais lattice, which is why the deviation is 0. Now, the deviation with primitive cubic is maximum, and so the crystal that is represented by this diffraction pattern is most like the primitive triclinic and very far away from that of the primitive cubic. So using the program, you can find out which is the best fit Bravais lattice that corresponds to the crystal. To recap about Bragg's law of X-ray diffraction, which we had studied in the previous class, the derivation of the Bragg's law came from, I'll just quickly go through the derivation once more. So if there are two incident beams, ray 1 and ray 2, ray 2 is traveling a certain distance extra. Like this distance that I'm showing, this is the extra distance that ray 2 is traveling compared to ray 1. Now, if we want to measure this distance, what we do is that this incident angle, we label it as theta or the Bragg's angle. And the distance between the crystallographic planes, we call it d. So this distance is d sine theta, and this is also d sine theta. So ray 2 is traveling an additional distance of 2d sine theta compared to ray 1. Now this additional distance, if it is an integral multiple of the wavelength, then there will be a constructive interference between ray 1 and ray 2. So in constructive interference, basically both the peaks are at the same point and the troughs are also at the same point. So the resultant wave has an amplitude twice that of each of the individual waves. So only if this extra path difference corresponds to a distance of which is an integral multiple of the wavelength, will constructive interference occur. If it is not so, the waves will destroy each other, and that is destructive interference, in which where there is the peak of one wave, there is the trough of the other wave. So the condition for getting good intensity diffraction spots is that this path difference, or 2d sine theta, is an integral multiple of lambda. And n, the integer, is called as the order of reflection. So when n is 1, we say it is the first order of reflection. So in Bragg's law, there are certain conditions that must be met. One is that the incident beam, the normal to the reflection plane shown by this dotted line, and the diffracted beam are always coplanar. In this case, they are all in the plane of this slide. The angle between the diffracted beam and the transmitted beam is usually 2 theta. So this is the diffracted beam. And if the incident beam had passed through without any deviation, that would have been the transmitted beam. The angle, as you can see, theta, and this angle is also theta. So the total angle is 2 theta. And since you know that sine theta cannot be more than unity, so n lambda must be less than 2d. And for n equal to 1, lambda must be less than, the wavelength of the X-ray must be less than 2d. And since d is very small, which is the distance between the crystallographic plane is very small, that is why this wavelength, according to the Bragg's law, falls within the X-ray wavelength range. And so visible light can't be used for X-ray crystallography. This is another treatment of Bragg's law, where if we consider the X-rays incident at an angle theta on one of the lattice planes and study the scattering of these X-rays from adjacent lattice points. So in the previous treatment, we had studied the diffraction from one atom on this upper plane and one atom in the lower plane. So two different planes. Now we are studying the diffraction between two atoms on the same plane. So in this case, there will be constructive interference of the waves scattered from two successive lattice points A and B if the distances AC and DB are equal. So as you can see, this first ray travels a distance AC and the second ray travels a distance BD. So if these distances are equal, then the phases will remain the same when they eventually meet each other at the detector. That is, there will be constructive interference. So constructive interference scattered from the same plane occurs if the scattered wave makes the same angle as the incident wave. So you can see the incident wave makes an angle of theta, and the scattered wave also makes an angle of theta with the plane. And if you extend the incident wave, then it is 2 theta. So this is another treatment of Bragg's law, in which basically in the previous treatment, you had considered this path difference, which was 2d sine theta. And here the path difference for one wave is BD and another wave is AC. So once these two are equal, there will be constructive interference and you will get high intensity diffraction spots. Now that we know all about the Bragg equation, we will talk about the Lau equation and the Lau conditions. So consider a crystal lattice, the unit cell of the crystal lattice. And you know that for a three-dimensional lattice, there are 6 parameters: A, B, C, the sides, and alpha, beta, gamma, the angles. So any atom in this lattice can be represented as X equal to PA plus QB plus RC, where P, Q, and R are constants, and A, B, and C are the dimensions of the unit cell. So you can represent any atom in this crystal with this formula. Now, if you consider K in to be the wave vector of the incoming incident beam. So if you consider this incident beam that is coming towards the crystallographic plane as K in, and K out to be the wave vector of the outgoing or diffracted beam. So the beam that is diffracted, this is K out. And you considered a difference vector, which is the difference of these two vectors, called delta K. This is called the scattering vector or the transferred vector, and it measures the change between the incident and the diffracted beam. So there are certain conditions that this scattering vector delta K must satisfy, and these are known as the Lau conditions. So these conditions are basically, if you do a dot product between the unit cell dimensions. So A, B, and C are the unit cell dimensions. And if you dot product the A, B, and C with the delta K, which is the scattering vector, that should give you a constant, which is 2 pi into H, K, and L, where H, K, and L are the Miller indices. So basically, where does this come from? Here you are dealing just with a one-dimensional system. So in this one-dimensional system, if you consider the difference in the distance traveled between the diffracted and the incident rays, you can see that this difference is AB minus CD. So these two rays, if you consider the journey of ray 1 and the journey of ray 2, the difference between the lengths that they have traveled is AB minus CD. And if you, from trigonometry, you can see that AB minus CD will eventually turn out to be a function of this basis vector A. So, if you extend that to 3 dimensions, you will see that this difference vector can be multiplied with A, B, and C to get these constant values, which is a product of 2 pi and the Miller indices H, K, and L. So like this, you can, for each h, k, and l, you can get a scattering vector. So you know that you can have infinitely different h, k, and l. For each plane in the crystal, there is a different h, k, and l. So according to that, you can have infinite scattering vectors, and all these scattering vectors will give you the net diffraction pattern. So how is the Lau equation and the Bragg's law related? You had learned in the previous class that real space is said to be the space that the crystal lattice occupies. And from this crystal lattice, you have a crystal structure and a unit cell. Now, if you pass an X-ray through the crystal lattice, you will get a diffraction pattern. And you can solve the diffraction pattern to get what is called a reciprocal lattice, which occupies the reciprocal space. So here you can see this is the real space where the arrangement of atoms of the crystals are occupied. And this is the reciprocal space, which is the solution of the diffraction pattern. Now there is a relation between these two, that is they are inversely related. So if say a side like you can see this is a two-dimensional lattice. So the side of the two-dimensional lattice unit cell parameter is A. But in the reciprocal lattice, it will be 2 pi by A. So if A is long in the real lattice, it will be short in the reciprocal lattice because it is inversely proportional. So that is how the real space and the reciprocal space are related. Now, if we consider a reciprocal lattice vector defined by G, which is HA plus KB plus LC. So basically G is a reciprocal lattice vector and it is defined by A, B, and C, which are the basis parameters of the reciprocal cell, and HKL are the Miller indices. Now, if you multiply G with X, so X is any point on the crystal lattice, as you saw in this previous slide, that X is defined by PA plus QB plus RC. So if you multiply G, the reciprocal lattice vector, which is defined by HA plus KB plus LC, with X, which is any point in the real lattice, defined by PA plus QB plus RC. Now, if you multiply this dot product, what it does basically is it will multiply the X terms of both, the Y terms of both, and the Z terms of both. So if you multiply HA into PA, now you know that so A is the unit cell dimension of the reciprocal lattice and small a is the unit cell dimension of the real crystal lattice. So as you can see here, small a, and here it is 2 pi by A. So if you multiply these, you will get a value of 2 pi. So if you multiply HA with PA, you will get 2 pi, and so capital A into small a will give you 2 pi, and you will have HP remaining. So it is 2 pi HP. The second term will be KB into QB. So capital B into small b will give you 2 pi, and you will have KQ remaining. And similarly for the third term. So basically G into X is giving you 2 pi into N, where N is a constant, which is defined by HP plus KQ plus LR. So the interesting point in this is that you have now arrived at the Lau equation. So we had seen in the previous slide that delta K is the vector difference between the diffracted beam and the incident beam. And here you can see that delta K is also equal to G. So this is sometimes called as the Lau condition. As I said, that diffraction patterns are a way to experimentally measure the reciprocal lattice, which is from the diffraction pattern, you will not get the real lattice directly, but you will get the reciprocal lattice. And the reciprocal lattice is inversely related to the real lattice. So you can just invert the pattern and get the pattern of the real lattice. So for any point, so what you have found here is that delta k is g. Now, if you multiply delta k with x, and you know that x is PA plus QB plus RC. So here you will get delta k into A. And you saw in the previous slide that delta k into A is 2 pi h. So if you multiply delta k into A, you get 2 pi h and P. Similarly, delta k into B is 2 pi k and delta k into C is 2 pi L. So you're applying the Lau equation over here. You take 2 pi common and you will again have HP plus KQ plus LR, which is a constant N. So you can say delta K into X is 2 pi N and GX is also 2 pi N. So delta K is basically G. And this is what is called as the Lau condition. Now, if you rewrite the Lau condition, that delta K equal to G that you derived in the previous slide, you can write that out as K out minus K in is G. If you take the magnitude of these vectors and square them, you will get this equation where the magnitude, like you have moved K into one side, so K out minus G, and you square both sides. And then you expand this square. So you get K out whole square plus G whole square minus 2 K out into G. There is something called the elastic scattering condition, which says that the energy of the incident beam must be equal to the energy of the diffracted beam. That is, there is no energy that is being absorbed or lost. So in that case, K out whole square is K in whole square. So if that is so, then these two will cancel out. And if you move the 2k out g term to one side, you will have 2k out g is mod of g whole square. So in a way, this is like the conservation of momentum equation, which is basically 2mv is half mv squared. So this is a similar equation to the conservation of momentum equation that is there in physics. Now, since the angle between K out, so here the vectors are clearly shown. So K0 is the incident beam, K is the diffracted beam, and delta G or K is the difference between the incident and the diffracted beam, which is this arrow. So altogether, these three form an isosceles triangle in which if you consider this normal that is bisecting the triangle, this is theta, this is 90. So this must be 90 minus theta. So the angle between the diffracted beam and G is 90 minus theta. So if that is so, then you can rewrite this as K out into G is mod G squared divided by 2. You are bringing the 2 to this side. And so you can write that as K out into G into cos of 90 minus theta. So how is this written? You will base just 1 second. My net is, there's a problem with my internet. Yes, right. I'm reconnecting again. So you know that, like I said, the angle between the diffracted beam and this G or the delta K scattering vector is 90 minus theta or pi by 2 minus theta. So the definition of dot product is that K out minus G is the magnitude of K out into the magnitude of G into cos of the angle between the two vectors. The angle between k out and g is 90 minus theta. So you can rewrite this as mod k out into mod g into cos of 90 minus theta is basically sine theta. So there are two equations that you have found. One is that 2k out into g is mod g squared, and another is 2k out g sine theta is also mod g squared. So you can now replace the values of k out with 2 pi by lambda and mod g by 2 pi n by d. And if you replace these and you cancel out the 2 pi n and you rearrange these on either sides, you get the Bragg's equation, which is 2d sine theta is n lambda. So starting from the Lau condition, you can arrive at the Bragg's equation. So both these laws are very fundamental and they are correlated with each other. This is another look at the real and reciprocal lattice vectors. So from the concept of the reciprocal lattice, we know that each reciprocal lattice vector is an integer combination of the three reciprocal basis vectors. If you are defining any vector in the reciprocal lattice, you will define that like if it is H, you will define that as H A star plus K B star plus L C star. A star, B star, and C stars are the basis vectors of the reciprocal lattice, and any point in the reciprocal lattice can be defined in terms of these basis vectors and the HKL Miller indices. So you have two lattices. One is the actual crystal lattice having the sides A, B, and C, and another is the reciprocal lattice having the sides A star, B star, and C star. So you need to know the relation between A, B, C and A star, B star, C star. The relation is basically, it is related by a cross product. So if you take a cross product of B and C in the original crystal lattice and you divide it by the volume of the unit cell, you will get the vector value of A star of the reciprocal lattice. So what these equations give you is that from the diffraction pattern, you will derive the reciprocal lattice. And from the reciprocal lattice, using these equations, you can find the real lattice vectors A, B, and C and reconstruct the real lattice. So, so far you have seen the Lau condition for diffraction, and now we will study something called the Ewald sphere. So the Lau condition requires that the three vectors, which is S0, the incident vector, S, the diffracted vector, and H, which is the difference between the incident and refracted vectors, they must form a triangle with two equal sides. Now, if you construct a sphere with the center at the origin of S0, so you can see here a sphere has been constructed and the origin of the incident vector S0 is the center of the sphere. And the magnitude of S0 is the radius. So this is the magnitude of S0 and it is the radius. Then the diffraction condition is satisfied only if the end point of a reciprocal lattice vector H is located on the surface of the Ewald sphere. So H is the difference between the incident and diffracted beams, and you can also call it as a reciprocal lattice vector. So the condition of diffraction is satisfied only if H, so you know that H has to start at the surface of the sphere because H starts from the endpoint of S0, but H must also end at the surface of the sphere. So that is the condition that is there for getting a good diffraction spot. and the direction of the diffracted beam, which is S, is shown here. So by changing the direction of H, we can get many different S, and according to each S, we will get a spot on the detector. So based on the evolved sphere, it is clear that each reciprocal lattice vector H can give rise to a diffracted beam if the reciprocal lattice takes different orientations. So H can have, over here, H is oriented in this way, and that is why the output diffracted beam must connect S0 and H, and it is in this direction. H can have infinitely different directions, and according to that H, you will have a corresponding direction of S, and you will get different corresponding spots on the detector. So this is the evolved condition of diffraction. So for a monochromatic beam, the crystal has to be moved relative to the incident beam in order to generate different diffraction peaks. So as I was saying earlier, that when you are mounting the crystal on the goniometer, it has to be mounted at different angles to get the picture of the crystal from different sides. So now that you have learned about the diffraction pattern, you have to learn about something called the structure factor. So what the diffraction pattern gives you is basically the maxima of the electron density function rho xyz. So so the diffraction pattern gives you an idea of the electron density, and the electron density will give you the idea of the location of the atom, that is the internal structure of the crystals. Now the electron density is present in the real crystal, so it is part of the real space. It is related to the reciprocal space through something called as the structure factor, written as FHKL. So FHKL represents the diffracted waves which, when colliding with a photographic plate or detector, leave their mark in the form of the spots in the diffraction pattern. So basically the spots in the diffraction pattern correspond to FHKL, which is a measure of the amplitude of the wave, of the diffracted wave. This amplitude is multiplied with the phase. So amplitude, as you know, is the distance from this baseline to the top of the wave, and phase is the horizontal shift. So you need both the amplitude and the phase. Here is an equation that correlates the amplitude and the phase of the diffracted wave to the electron density function. So basically how this works is that from the diffraction pattern, you know the intensity of the spots, and intensity is basically amplitude squared. So from intensity, you can get this amplitude. But finding the phase is a problem. This is something we will discuss in the subsequent slides. But once you find the phase, you can integrate it over all the spots and divide by the volume of unit cell to get the electron density. And once you have the electron density, you can have an idea about the atomic structure within the crystal. So now we will look deeper into this structure factor. So structure factor, or FHKL, is the resultant of all waves scattered in the direction of HKL reflection by n atoms contained in the unit cell. So structure factor is a summation. For each atom, you are summing up this term Fi and this term, which is e to the power 2 pi I, and then the position of the atom. So the position of each atom is defined in terms of x, y, z coordinates and HKL Miller indices. So this is a property of the position of the atom. And this term Fi is an electronic property of the atom. and it is called the atomic scattering factor. The scattering factor is essentially describing the amplitude for the scattering by each atom. Fi is completely independent of the position of the atom, and it only depends on the type of atom. So as you can see, this is a graph of this small fi with sine theta by lambda, where theta is the Bragg's angle. So at sine theta by lambda 0, the F is maximum and it is equal to the number of electrons in the atom. So if you have scattering from a carbon atom, you know that carbon has 6 electrons. So the value of F will be 6 at sine theta by lambda 0. And as the sine theta by lambda increases, the F value will slowly decrease. Generally, in proteins, you have the same common atoms, which is carbon, nitrogen, oxygen, and hydrogen. So the F will be same for each type of atom. So there is a similarity in the diffraction pattern in proteins. So now we looked at details at what is the structure factor. So now we also have to look at the detail of the phase. So if you consider the Bragg's law, this is a crystal formed of two kinds of unit cells. One is this red atoms, which can form a red parallelogram unit cell, and another is the blue atoms, which can form a blue parallelogram unit cell. So according to the Bragg's law, the phase difference between two reflected red beams will be 0 degree. So if you consider diffraction only from the red atoms shown by these red rays, the phase difference between them will be 0 or 2 pi, which is 2 pi basically means your 360-degree rotation. So which is basically equal to 0. And again, these blue rays will have a phase difference of 2 pi. So only then the Bragg's law is fulfilled. However, between the red diffracted ray and the blue diffracted ray, there is a certain horizontal shift. So if you can see here, the peak of the red wave is not exactly corresponding to the peak of the blue wave. So there is a certain horizontal difference in phase, and you are defining that as delta phi. So the final diffracted pattern that you will get by summing up the red and blue diffracted beams will not be the exact sum of the amplitude, because there is a difference in phase. So you can see, if you want to calculate this phase difference is basically a multiple of 2 pi. So how do you arrive at that? For that, you can see that if you do A by H, A is basically the distance between this phased A by H is the difference, horizontal difference between your red lines. So A by H corresponds to 2 pi because it has to fulfill the Bragg's law. Similarly, B by K, which is the vertical difference, must also correspond to 2 pi. And similarly for C by L. And another thing is that if you take the difference between the red and the blue lines, which is the phase difference, phi A, it is corresponding to X. So if you divide these two and then you add them up, you will find that this pi difference, which is the difference between the red and blue waves, is a multiple of 2 pi. And if you consider x by a as x, y by b as y, and z by c as z, you can consider this because a, b, and c are essentially constants. So you can just shift the coordinate system x, y, z by that constant, and you will finally get this equation. which is relating your phase difference between the red and the blue lines with the coordinate system XYZ. So you have found that the phase difference between in this combined system. So you have a combined red and blue system, and you have found the phase difference from the previous this final equation. So now if we look at the structure factors, so the net structure factor is basically the summation of these individual structure factors. So if you have F1 and F2 from the red and the blue crystals, the net structure factor defined by capital F HKL is the vector sum of these two. And the definition of vector sum is basically you are summing up the x components, which is the x component of F1 is F1 cos phi 1, and the x component of F2 is F2 cos phi 2. You are summing up the x components and squaring them, and summing up the y components and squaring them, and taking a net square root to get the magnitude of the structure factor. This is the basic formula of the sum of two vectors. And the angle, net angle, which is the angle of this net structure factor with the horizontal axis, it is called as phi. And it is also defined by this formula, which is tan inverse of F1 sine phi 1 plus F2 sine phi 2 by F1 cos phi 1 plus F2 cos phi 2, where F1 and F2 are the individual amplitudes of the resulting waves in the red and blue crystals, and phi 1 and phi 2 are the individual phases of the red and blue waves from the crystal. So from each of these, you can sum up this red diffracted beam and the blue diffracted beam to get the net structure factor, which is the amplitude of the resultant diffraction spot defined by this formula. So this is shown just for two kinds of atoms. So if you have n kinds of atoms, you will just sum up, like there are j kind of atoms, you are summing up over j. That is the general case. So we have used vector representation to deal with the diffraction waves. So FHKL, if it is, so the structure factor is FHKL. The magnitude is shown by this arrow, and the phase is shown by the angle with the horizontal, which is phi. If you divide this into two components, the horizontal component and the vertical component, the horizontal component will be F cos phi and the vertical component will be F sin phi. Now, Euler equation formula states that any number which is e to the power ix can be defined as cos x plus I sin x. So since you have FHKL defined in terms of x and y components, you can use the Euler formula to convert FHKL into this form, which is a summation of Fj, the atomic scattering factor, and e to the power 2 pi I hx plus ky plus lz. And you sum up over the j atoms. So you can use Euler formula to convert FHKL into a simpler form. Now that you have the FHKL, something called an inverse Fourier transform is used to transform it into the electron density function, because ultimately you need the electron density. So we have different waves of X-rays superimposed on one another during diffraction. But we need to isolate the contribution of each diffraction so that we can find the net atomic structure. To solve this problem, a mathematical tool known as the Fourier transform is used. So this is a representation of the Fourier transform. Basically, you will have a net from the diffraction spot. You can get the waveform of the net wave pattern. So if you have, say, n atoms, there will be n diffracted rays, and the n diffracted rays will combine to give you a combined wave pattern. If you decompose this wave pattern into 3 component waves in this case, in a case of a crystal, you will decompose it into n component waves. So this is called a Fourier transformation. This decomposing the net wave pattern into the component waves is called the Fourier transformation. And these component waves are all unique, and they will have different frequencies and different amplitudes. So if you can decompose this, then you will find the contribution of each atom, and you will be able to find this electron density. Since different lattice spacings will diffract X-rays differently, each decomposed sine wave will give us a characteristic of the crystal structure. So performing this inverse Fourier transformation will give us valuable information on the crystal structure. Now I'll come into details of the phase problem. To calculate an electron density map, both the intensity and the phase is required. So if you look at the formula of the electron density, this is the structure factor, which basically F squared is the intensity. So square root of intensity is the structure factor, and phi is the phase. So both are required to get the electron density. From an X-ray diffraction experiment, you can measure the amplitude, and amplitude square is intensity. But it is almost impossible to measure information about the phase. So if you look at the structure factor formula, this magnitude of FHKL is the amplitude of the wave, which is the distance from the base to the peak. And phi is the phase, which is the horizontal difference between two waves. Finding this phase is the problem. So if we draw a figure showing the atoms in different color like this, it shows how the phase and amplitude of the overall scattered wave arises from individual scattered waves. So from each of these 4 atoms, there will be a different diffracted ray. So you're representing the diffracted ray by that corresponding color. So the diffracted ray from the blue atom is shown in blue, from the pink atom in pink, and so on. So if you place them one after the other, the rule of vector summation is that if you have 4 vectors like this placed end to end, then the summation of all vectors will be the vector that closes this, that forms a closed structure. So basically, after the 4 vectors, this was an open structure. And if you draw a line segment from the initial to the final vector, that is the this black line segment, that is the magnitude of the summation of these 4 vectors. So that is the rule of vector summation. What is meant by I and R is that the length of this arrow is the magnitude of the amplitude of this scattered wave, and the angle with the horizontal is the phase. So the magnitude of this net vector can be calculated from the intensity of the diffraction spots. So this is your net diffracted ray from these 4 atoms, and the magnitude can be found from the intensity of this spot. So if you take square root of intensity, you can find the magnitude of the net diffracted ray. But any information on the phase is lost. So what is required now is to find a solution to the phase problem. So what do we know? We know the position of, so for each of these spots in the diffraction pattern, you have an HKL value. So you know the position. And each of these spots have an intensity. So you know the intensity. And from square root of the intensity, you know the structure factor magnitude. What is missing is this phase information. So this is a representation of the atom and its Fourier transform. Note that both the atom and its Fourier transformation have circular symmetry. But the atom is a very sharp point and the Fourier transformation is kind of blurry. So if you extend this to crystal, the Fourier transformation of a crystal will give you the diffraction pattern, and the Fourier transformation of the diffraction pattern will give you the crystal. So in experiments, what happens is you have the diffraction pattern. You need to carry out a Fourier transformation to get data on the crystal. So there is a way to solve the structure even in the absence of phase, and that is called the Patterson function. So the structure of small molecules may be solved even in the absence of phase information. So the structure factor magnitude alone can give you information about the electron density. This information can be accessed by calculation of the Patterson function. The Patterson function is obtained by calculating a map using the squared structure factor magnitude and all the phases set to 0. So if you set the phase to 0, so phi is 0, and you expand e to the power minus 2 pi I using the Euler formula. So e to the power ix was cos x plus I sin x. So if you expand it using that formula, considering phi 0, you will get this equation, and that is what you are is called the Patterson function. So instead of peak at the atomic position, the Patterson map shows peaks at every position that corresponds to an interatomic vector in the structure. So basically, in normal diffraction patterns, you get peaks corresponding to the atoms. And in the Patterson function, you will get peaks corresponding to the interatomic relations. So if you consider an interatomic vector, so this is the crystal structure, and you consider an interatomic vector from the middle atom to this side atom, the Patterson function will give a peak corresponding to this. So it is basically the relationship between atoms that is shown by the Patterson function. However, it is applicable only for structures of around 20 to 50 atoms. So there is because you are taking a very big assumption, which you are assuming the phase is 0. And if the structure becomes larger than 20 to 50 atoms, this assumption becomes wrong. So in Patterson function, instead of the structure factor, you take the square of the structure factor and you consider the phase as 0. Then you can get from the electron density, you can get the Patterson function. And the Patterson function can be calculated directly from the diffraction pattern, because the diffraction pattern gives the intensity, which is this F square, and the HKL of each of the spots. So the Patterson function can be obtained directly from the diffraction pattern. So as I discussed, the peaks in the Patterson function correspond to these interatomic vectors. And the value of the function is proportional to the product of the atomic numbers. So if you have heavy atoms, that will give a good Patterson map. Or if you have a large, because the heavy atoms have a large number of electrons, and from each of the electrons, there is a diffracted ray. So suppose the crystal space is defined by the electron density function, and at every point in the unit cell, the atoms are defined by, say, x1, y1, z1, x2, y2, z2, and so on. In Patterson function, the peaks are defined by a subtraction. So U is x1 minus x2. V is y1 minus y2. So if you subtract the positions of the atoms, you will get the peaks of the Patterson function. Because Patterson function is basically showing the positional correlation between two atoms. So if you subtract the x coordinates, the y coordinates, and the z coordinates, you will get the coordinates of the Patterson map. So in a Patterson function, if there is a vector from atom 1 to atom 2, then there will be another similar vector from atom 2 to atom 1. So Patterson function always has a center of symmetry I. So Patterson function is a way of solving the phase problem by considering the phase 0. But it is only applicable for small molecules. So if you want something that is applicable for larger systems, one of the methods is introduction of a heavy atom or isomorphous replacement. So in isomorphous replacement, what happens is that, hello?
Yes, ma'am, you are audible.
Okay. So in isomorphous replacement, what happens is that if you look at this structure, where this white atom is potassium, these purple atoms are manganese, and the red atom is oxygen. So isomorphous replacement means you are replacing some of these manganese atoms to have ruthenium. So the structure of the crystal is not changing, which is why it is called isomorphous replacement. But what you are doing is that you are replacing one atom by a much heavier atom, which has many more electrons. So since you are replacing it by a heavy atom, as you know, the diffraction pattern from a heavy atom is very intense and clear. So if you have a weak diffraction pattern and you carry out isomorphous replacement, you will the weak diffraction pattern will become strong. So normally multiple isomorphous replacement is done. So multiple of the manganese are replaced by ruthenium. So how this is done is that for protein crystals, this method is conducted by soaking the crystal of a sample to be analyzed with a heavy atom solution or co-crystallization with the heavy atom. And the addition of the heavy atom should not affect the structure because it is fitting into the spaces of the atom that it is replacing. So this replacement should be isomorphic. So basically, if you see the diffraction pattern from the protein crystal, this is the net amplitude of the diffracted beam. And if you have the diffracted pattern of the co-crystallized protein crystal and heavy atom, you will have two diffracted beams, FP, which is from the protein, and FH, which is from the heavy atom. So the net diffracted beam that you will observe, FPH, is the summation of FP and FH. So in terms of diffraction pattern, one second. If you see the diffraction pattern, it will be a summation of the diffraction patterns of the protein and the heavy atom. So single isomorphous replacement is basically replacing just a single atom with a heavy atom. And here the vector summation is relatively simple. So you have this FP, which is for the protein, and FH, which is for the heavy atom. FPH is the resultant diffracted beam from the net co-crystallized protein and heavy atom. So you can, if you find FPH and you subtract FP, you can find that what is, so here if you see, you have the diffraction pattern from the co-crystallized heavy atom and protein, the diffraction pattern only from the protein, And if you subtract them, you will find the diffraction pattern from the heavy atoms. But the problem that arises in single isomorphous replacement is that there is a phase ambiguity. So since you know the magnitude of Fp, but you don't know the phase, Fp can point upwards or downwards. Suppose you are not sure about the sign of the phase, so which is alpha p, Fp can point either upwards or downwards. So if you solve this phase angle, you will see that there are two possible phases. And this is basically where the phase ambiguity arises. But if you have multiple isomorphous replacement, so you have Fp, which is from the protein, and FH1, which is from the first heavy atom. So this is FPH1, which is from the protein and the first heavy atom. Similarly, from the protein and the second heavy atom, you will have another vector. So if you add these two vectors, FPH1 and FPH2, there is only one possible net vector, and so there is only one possible amplitude. So more the number of heavy atoms, more this phase ambiguity is reduced, and you can predict the phase with more accuracy. So these two protein diffraction patterns are shifted vertically with relative to one another. Here you can see that there are some lighter spots which are of the protein, and there are some darker spots which are vertically shifted, which are from the co-crystallized protein and heavy atom. So there are a few things to note. One is that the intensity is changing when it is a protein and heavy atom. And secondly, the overall shape is the same, which suggests that the heavy atom has taken part in an isomorphic replacement. So the structure of the unit cell of the crystal is not changing. So you can use the differences between these diffraction patterns to find information about the phase. So this formula tells you that how many heavy atoms need to be added to get an intense enough diffraction spot. So NH and NP are the number of heavy atoms and the number of protein atoms. And ZH and Z effective are the atomic numbers of the heavy atom and the effective atomic number of the protein. So the average of all the atomic numbers of the atoms in the protein. So if you do that, you can find what was the ratio of the change in amplitude by the original amplitude. So if you do this calculation for a mercury atom, you can see that for one mercury atom added to a protein of 1000 atoms, the structure factor difference is 25%. So there is an increase in intensity by 25% just by adding one heavy atom to such a large protein. But to be sure of the phase and to clear any phase ambiguity, it is always good to do a multiple isomorphous replacement. Another is the next thing that we'll go through is the anomalous dispersion affecting the scattering factor. So we had learned about the scattering factor that is unique to each atom, and it depends on the atomic number and the angle of scattering. Now, if your incident X-ray has a frequency close to the natural oscillation frequency of the electrons, there is something called anomalous dispersion. So if you look at the atomic structure here, you have a high energy X-ray, which is enough to promote one of the 1s electrons to the empty 5s orbital. A low energy X-ray will not be able to do this. So in this case, when you have a high energy X-ray, there is an absorbance of the X-ray. So far, we were talking about elastic scattering conditions. So the energy of the incident X-ray was equal to the energy of the diffracted X-ray. But now what happens is if you have a X-ray with high enough energy, some of the energy of that X-ray will get absorbed. And then what will happen is that your structure factor will change. So the structure factor, which was initially F0, is now changed by two terms, F prime and F double prime. F prime is the real part and F double prime is the imaginary part. Now, if you, so this change generally occurs for heavier atoms. So the relatively light atoms found in protein like carbon, nitrogen, oxygen, and hydrogen do not contribute to this scattering. And in order to observe this anomalous scattering, a heavy atom must be added. And the X-ray wavelength should be close to that of the heavy atom absorption wavelength. So if that is done, then the Friedel's law will break down. So what Friedel's law states is that the reflection from HKL and minus H minus K minus L planes are equal in amplitude and opposite in phase. So this is a representation of the Friedel's law. You have a diffraction from HKL plane and a diffraction from minus H minus K minus L planes. The length of these two vectors are same, but the phases have opposite signs. So this is Friedel's law. But if you have an anomalous scattering, then the Friedel's law is no longer valid because you have the scattering from protein Fp, the scattering from heavy atom Fh. On top of that, if you add the anomalous scattering F double prime, you will find and you look at the net vectors of the co-crystallized protein and heavy atom, the length of the vectors become different. So the Friedel's law, that is the magnitude of the amplitudes should be same from HKL and H minus K minus K minus L. It is no longer valid. So in anomalous, whenever there is an anomalous dispersion effect like this, that is the energy of the X-ray is absorbed and then it is diffracted, this Friedel's law is no longer valid. So we can take advantage of this to find the phase through a method called multiple anomalous dispersion or MAD. In this technique, the atom's inner electrons or bound electrons absorb X-rays of particular wavelengths and re-emit the X-rays after a delay. And this causes a phase shift known as the anomalous dispersion effect. So analyzing this phase shift results in a solution for the phase. So basically you have there are two different kinds of X-rays that are diffracting. One is from the free electrons, which are directly incident and diffracting, and another from the bound electrons, where the X-rays come, get absorbed, and then are diffracted with a phase shift. So finding the difference between these, you can use this phase difference to find the difference in position of the bound and free electrons. So how this can be done is by incorporating a heavy atom into the protein. But another method is the incorporation of selenomethionine. So whenever there is a methionine amino acid in the protein, you can replace the sulfur with selenium. And so selenium is a heavier atom than sulfur and can take part in this anomalous scattering. So proteins that do not contain selenomethionine can simply be grown in a medium which contains selenomethionine, and the selenium and atoms will carry out this anomalous dispersion effect. So you have seen the Patterson function, the multiple isomorphous replacement, and the anomalous dispersion effect to find the phase. Once the phase is known, the exact values of the phases can be improved by certain methods. So one is the solvent flattening, which is basically the electron density of the solvent is 0.33 E, where E is the charge on a single electron. And for a protein environment, it is 0.43. So what solvent flattening does is that it defines the protein solvent boundary, and wherever protein is not present, it sets that value to that of the solvent of 0.33. So if you do that, then the boundaries of the protein become very well defined, and so the phases or the atomic positions are defined properly. Earlier, there is a blur between at the boundaries. So the atomic positions at the boundaries are not very well known. But once the solvent flattening is done, the boundaries are well defined. The second method is the histogram matching. So from isomorphous replacement, you get an idea about the electron density in the crystal. You can match this electron density pattern to refine it and get a more precise definition of the atomic coordinates. The third one is the non-crystallography symmetry averaging. So a symmetry operation that is not compatible with the periodicity of a crystal pattern is known as a non-crystallographic symmetry, which basically means, so if you look at these three ducks, the ducks in this circle are symmetric, but they are not within the unit cell of the crystal. And so you cannot carry out any symmetry operations within the unit cell itself. So that is known as a non-crystallographic symmetry. What this method does is that it imposes equivalence on electron density values when more than one copy of a molecule is present in the asymmetric unit. So basically, if you have derived the electron density of A very accurately, you can use it to predict the electron density at B and C. So based on the prior knowledge of the electron density of A, the electron densities of the other structures can be found. Just 1 minute. So phase improvement basically means that once you know the phases, you can refine them to get more accurate structures. Another method of solving the phase problem is molecular replacement method. However, it requires the existence of a previously solved protein structure, which is similar to our unknown structure from which the diffraction data is derived. So you can get the similar structure from a homologous protein or from a lower resolution protein NMR structure of the same protein. So molecular replacement consists of 3 steps. Firstly, the determination of relative orientation of identical unknown structures in the same or different crystals. So if this dark blue is your reference protein and this light blue is the protein for which you are finding the structure, you have to find the rotation angle between these two that will allow these two structures to superimpose. Then the use of information from step 1 to determine the position of the local non-crystallographic operators relative to the crystallographic symmetry elements. The second part is that to find any translational operators to find the neighboring, like as I had talked that from one duck in A, you can find B and C by translation. So once you know the structure of this, by translation or T, you can find the structure of neighboring non-crystallographic elements. So using this, you can find the phase of your unknown protein. So in this, basically from the phase of the known protein, you are searching, carrying out a 6-dimensional search. So rotation in 3 degrees and translation in 3 degrees. So from the phase of the known protein, you are finding the phase of the unknown protein by finding that by how many degrees it is differing in rotation and translation. But for the molecular replacement, you need a good search model. So a good initial model is required from which you will compare the unknown protein. So generally, the rule that is used is that the sequence identity must be greater than 30%. So for the known protein and unknown protein, they must match by around 30% of the amino acid residues should match. And the signal to noise must be reduced. So in the unknown protein, if there are any structures that are not matching with the known protein, like water molecules or flexible side chains, that needs to be removed. The third step is something called a software known as Collaborative Computational Project number 4. So there are various programs in this CCP4 software to find a good search model. And finally, there is a program called MolRep for molecular replacement in the case where a homologous structure has already been identified. So the program will attempt to find the number of molecules expected in the asymmetric unit entered by the user. So once you have a good search model using CCP4, you can use MolRep to find so this is an output of MolRep. It will tell you that by what angles. So you can see the rotational relationship. There are 3 angles, phi, chi, and kappa. And also translation relationships. There is movement along 3 axes. So this output of MolRep will tell you by what rotational angles and by what translational distances the unknown protein differs from the known protein. And like that, you can find the phase of the unknown protein. Once the phases and structure factors and everything is known, then there is a refinement study is carried out, where basically the conformation that corresponds to the energy minimum is found. So the total energy, which consists of the summation of E conformation, meaning the energy of the bonded molecules and the energy of the non-bonded molecules, that is the van der Waals or electrostatic energy terms, and the energy of the X-ray. So these are added to find the total energy of the protein. And this total energy is minimized to find that what is the minimum energy structure. So one of the ways of this refinement is called a rigid body refinement. In that, you take the whole protein and you consider, say this protein consists of 2 rigid parts, rigid body 1 and rigid body 2. So these 2 parts, within the parts, there is no movement. But with respect to one part, the other part can move, and this movement is carried out to search for the minimum energy conformation. So the movement consists of 3 rotation and 3 degrees of translation, and a molecular dynamic simulation is carried out to find that what will be the minimum energy conformation. A positional refinement is basically, in rigid body refinement, you have rigidified 2 sections. In positional refinement, there is no such rigidification. For each point in the diffraction pattern, the atomic parameters X, Y, Z are optimized to get the minimum energy conformation. The problem with this is that there are so many variables that it is very difficult to do this positional refinement. So generally the rigid body refinement is preferred. Another kind of refinement is the occupancy refinement. So occupancy is the fraction of molecules in the crystal in which a given atom occupies the position specified in the model. So suppose the occupancy of a certain position is 50%. So the atom will exist in that position only 50% of the time. So occupancy is a measure of the movement of the molecule in the model. So suppose this tyrosine side chain is there. It is occupying this conformation 75% of the time and this conformation 25% of the time. So the occupation of this region will be 0.75 and this region will be 0.25. So like this, the occupancies are also refined to get an idea of the movement inside the molecule, protein structure. And there is finally something called as the B factor refinement. So B factor is an indicator of the atomic mobility. So and high value of the B factor indicates that that specific region is very dynamic or disordered. High values of B factor can also indicate that we have made a mistake in predicting the protein structure. Good protein structures should have a B factor within 20 to 30. If the protein B factor that we get from our diffraction pattern is higher than this, either it can mean that we have made a mistake because a protein cannot be that mobile that the B factor is so much greater than this, or it means that it is a disordered protein. So you have heard of something called intrinsically disordered proteins or IDP. So it can mean a high B factor can mean that it is an IDP. The B factor is an exponential expression applied to the scattering factor that relates to the thermal motion of the scattering atom and the decrease in scattering intensity that results from thermal motion. So basically, if you have a large B factor, like see, this is B0, B10, and B20. So as the B factor, so if you consider a certain, say 0.4, you can see that at 0.4, the scattering is minimum when B is 20. Scattering increases for B10 and scattering is maximum for B0. So with increase in mobility of the system or increase in B factor, the scattering is decreasing. And these are some applications of the B factor. So if you look at this plot, the highest B factor corresponds to the side chains, which is the red colors. And that is expected because the side chains are very mobile and they are free to move. But the main chain is held by peptide bonds. And so if you look at the main chain or the green lines, you can see that they are much lower. Another is application of B factor is homology modeling. So using the molecular replacement, if we compare a crystal structure with the model that we have built, we can see that at some places the B factor is very high. That means our predicted structure is wrong in these cases because the mobility cannot be that high within a protein. So it means wherever there is an unusual increase in the B factor, it means that that particular region of our predicted structures need to be refined further so that we can get lower B factors. Now, once you have your protein structure, there is something called an R value, which is a measure of the agreement between the crystallographic model and the experimental X-ray diffraction data. So R value is an idea of how good the structure is. So compared to the observed structure and the calculated structure. So R value is a prediction of whether you need to improve the structure or whether it is good enough. So when solving the structure of the protein, you first build an atomic model and then you calculate a diffraction pattern based on that model. Then the R value is calculated, and if it is around 0.2, it is good enough for the protein. But if it is 0.6 or higher, then the structure needs to be refined much more. There can be many reasons for a high R value. One can be that the protein and nucleic acid crystals contain large channels of water. So water is very mobile and it does not have a specific structure. So if there are a large number of water molecules in the model can have a lot of dynamism, which will cause us to incorrectly predict the model. And so the R factor will increase. The problem with using the R values is that the refinement process is often used to improve the atomic model of a structure to make it fit better to the experimental data. But this unfortunately introduces a bias into the process, since the atomic model is used along with the diffraction pattern to calculate the electron density. But so far, the R value is our best estimate of finding out whether our structure that we have predicted is good enough or not. Another molecular dynamics simulation technique to find out whether the structure you have is the minimum energy structure or not is known as simulation annealing. So in simulation annealing, what is done is that it is a molecular dynamic simulation, and what happens is that you travel along the energy profile. Suppose you start at point I. So your point K, if you move from I to K1, it is lower energy. So that you will always move. So the program always tries to find the lower energy. Now, however, if you only accept lower energy, then what can happen is that the program gets stuck in a local minima. So this is called a local minimum, but what we actually want to find is the global minimum. So in simulated annealing, the program works in such a way that if the energy is lower, it goes there. But even if the energy is higher, it can randomly go there. And so that enables it to find the global minimum. So this is the advantage of simulated annealing over other molecular dynamics simulation techniques, which basically in other molecular dynamics simulation techniques, it only goes to lower energies. And if that was the case, then the structure will get stuck in the local minimum. But in simulated annealing, it also goes to higher energies, and then eventually it finds the global minimum. So the basis of this simulated annealing is this formula, which is saying that the probability that the energy will increase by delta E is exponential of minus delta E by KT, where T is the temperature. So at lower temperatures, the probability of going to higher energy reduces till finally you reach a low enough temperature where it cannot go to any lower energies, and that is how the global minimum is found. So one thing you are assuming here is that the folded protein is the global minimum energy conformation. So simulated annealing takes more time than other molecular dynamic simulation techniques, because in other techniques, you are just always going to the lower energy states. But in simulated annealing, it goes both to lower energy and higher energy. And it keeps a record of all the energies that it has covered. So like that, it can locate the global minimum energy conformation, which should be the best possible conformation for the crystal. Finally, now that all the work of interpreting the X-ray diffraction data, forming a structure, refining the structure, and all that is done. So finally, the structure is deposited in the protein data bank, which we have learned is the single worldwide repository for the processing and distribution of 3D biological macromolecule structure data. So for deposition, the first step is to prepare the data using a resource called PDB extract. So that resource, what it does is that it assembles specific details about your experiment and experimental model from the coordinate and structure determination output files to prepare for the PDB deposition. The second step is that the structure is validated. So this service is designed to help you check your model and experimental files prior to start of deposition. So in data validation, the validation server checks whether the PDB structure is good enough to be deposited. And finally, there is something called ProCheck that assesses the geometry of the residues in a given protein structure compared with stereochemical parameters from well-refined high-resolution structures to see if your structure is as good as other structures in the PDB, and only then it is accepted. The general rule is that the resolution of the structure, if it is less than equal to 2 angstrom, that is a good resolution. And if the R factor is around 20 to 23% or 0.2 to 0.23, then that is a good enough structure. So that brings us to the end of this summarization.
এই যে ক্লাস চলছে
And so I will now go through some sample questions. The first one is that the measure of the agreement between the crystallographic model and the experimental X-ray diffraction data can be defined as. So what is the answer for this?
ম্যাম ইজ ইট আর ফ্যাক্টর
Yeah, you are correct. The correct answer is B. And so as we discussed, the rule of thumb to remember is that R factor of around
হ্যাঁ মা
uh,
পরে কথা বলছি
R factor of around 0.2 is good for proteins. So the next question is that phase associated with a crystal can be defined as.
alpha HKL.
Yes. So the correct answer is D. And if you look at the entire expression, so rho is the electron density, V is the volume of the unit cell, FHKL is the structure factor or the amplitude, alpha HKL is the phase, and the H, K, and L are the Miller indices. The next question is that which of the following parameters influence the atomic scattering factor?
Ma'am, the intensity of the X-ray radiation.
Okay, no, that is not correct. The correct answer is A. So there is a graph that you can remember is that this angular value sine theta by lambda, where theta is the Bragg's angle. So the atomic structure factor F is related to this angular value, like kind of an exponential relation. So when this angular value is 0, the value of the scattering factor is always equal to the number of electrons. So in carbon, it is 6. And as the angular value increases, the scattering factor decreases exponentially. So the correct answer is this angular value sine theta by lambda, where lambda is the wavelength of the X-ray and theta is the Bragg's angle. The next question is that structure factor can be defined as which of the following?
FHKL.
Yes, that is correct. So correct answer is D. And again, if you go back, so FHKL is the structure factor or the amplitude. What is the correct equation of Bragg's law?
N lambda is equal to 2d sine theta.
Yes, you're correct. The correct answer is A. So we have already studied Bragg's law in the previous class as well as this class. So I'm not going to go into the details. But yeah, that is the correct answer, that which is n lambda is 2d sine theta. Inverse Fourier transformation of the diffraction pattern gives us details of which parameter?
Ma'am, structure factor.
Actually, it is electron density. So you confused it with direct Fourier transformation. So direct Fourier transformation gives you from electron density to structure factor, and inverse Fourier transformation gives you from structure factor to electron density. So yes, so basically the structure factor or the amplitude is obtained from the diffraction pattern, and you carry out an inverse Fourier transformation to get an idea of the electron density, which is rho xyz. The next question is that in the expression of Bragg's law, which term describes the path difference?
Ma'am, 2D sine theta.
Yeah, you are correct. The correct answer is B. So the path difference is this distance, and it is a summation of d sine theta and d sine theta. So the path difference is 2d sine theta. Then heavy metal replacement to solve the phase difference can be defined as?
Ma'am, isomorphous replacement.
Yeah, you are correct. So this is the general principle of isomorphous replacement, where basically you get a diffraction pattern from the heavy metal plus protein and a diffraction pattern from only the protein. So then you will get to know the diffraction pattern of the heavy atoms. And from that, you can find out the position of the heavy atoms. And from the positions, you can find out that which are the spaces in the lattice that the heavy atoms are occupying. And that will give you an idea of the lattice structure. And this is known as isomorphous replacement. So generally, we do multiple isomorphous replacement or MIR, but single isomorphous replacement or SIR can also be done. The next is a mathematical question. So if an X-ray of wavelength 100 angstrom is incident on an atom at an angle of 90 degree, then what should be the D for the first order spectrum? So you can apply Bragg's law to this
50,
and so.
50 angstrom.
Yeah, you are right. So if you apply n lambda is 2d sine theta, so n will be 1 as it is the first order spectrum. So it becomes lambda is 2d sine theta. Then if you rearrange it, d is lambda by 2 sine theta. Lambda has been mentioned to be 100 and theta has been measured to be 90. So if you put those values, sine theta is 1. So D is 100 angstrom by 2, which is 50 angstrom. So you just have to be like look at what is the order of the spectrum and then put it in Bragg's law. The next is that the existence of a previously solved protein structure is needed for the following phase resolving technique.
Molecular replacement.
Yeah, you are correct. So like the principle of molecular replacement, as we discussed, is that you have a known protein structure and you superimpose the unknown protein structure and you find out what is the difference in rotation and the difference in translation. So using that, you can find out the phase of the unknown protein structure. Then it is that which program determines the best lattice fit to each point group.
Ma'am, is it indexing?
Yeah. So indexing is the program which basically it gives you an idea. So it will take all the 14 Bravais lattices and it will give a measure of the deviation from each of the Bravais lattices. So this particular crystal structure is primitive triclinic and so the deviation is 0. So if you look at the column for the deviation, you can find out which has the deviation 0, and that is the crystal structure that is coming from your diffraction pattern. And this program is called indexing. Next is, in a crystal, the ordered periodic arrangement of molecules produces dash interference.
Constructive.
Yeah. So like you can see, if you because of the periodic arrangement of the atoms, the constructive interference is happening, which is the peaks are at the same position and the troughs are at the same position. So you have your resultant wave, which has double the amplitude, that is the summation of the amplitude of these two waves. So that is constructive interference. Which of the following statements is false?
Ma'am, is it option D?
Yeah, you're correct. So as I talked in the beginning of the class, is that diffraction from a single molecule has very low intensity. And that is why we are using crystals for X-ray crystallography. So
Ma'am,
that,
is it the same cause we use MIR in case of
yes,
diffraction?
multiple isomorphous replacement has the same function.
Okay.
So yeah, so the diffraction from a heavy atom is much more intense than that from a light atom. And if you have multiple heavy atoms, the intensities will, there will be constructive interference from all the heavy atoms, and you will get an intense enough diffraction pattern. The final question is that which of the following program determines the intensities of each spot?
Ma'am, integrating.
Yeah, the correct answer is integrating. So the intensity of each spot is integrated to find uh, we talked that the intensities have a Gaussian distribution. So you have to integrate it over the Gaussian distribution to find the net intensity. So that is all the slides I have. So if you have any questions, you can clear them now.
Ma'am, I want to ask something, ma'am. The final exam, it will be
Hmm.
on MCQ based, or the subjective will be, questions will also be there?
So, like I said, last year it was completely MCQ based. So
Okay, ma'am.
this year I have not asked, but last year it was fully MCQ.
Okay, ma'am. And the weightage, like,
Weightage meaning?
yes, ma'am. The like how much, how like marks, ma'am? How
I'm not
much?
sure, but I think it was 100 questions, 1 marks each, I think. I
Okay,
will
ma'am.
just confirm that once.
Okay, ma'am. Okay, kindly
Mhm.
confirm that, ma'am.
Okay, fine. Um, there is a like lot of mathematics in this lecture, but you don't have to worry about that because most of the questions, as you can see, are like very simple theoretical type questions only. There isn't like you don't have to go into the mathematics too much.
Ma'am, like mathematics was like vector portion was there.
Huh.
Mostly it was like vector algebra.
Yes. So, like you, that is what I'm saying. If you look at the like example questions, we don't. It is just there in the summary of the portion. Like the example questions were much simpler. So maximum maybe you can be asked like four formulas will be given, and you will be asked that which is the correct formula, something like that. Nothing you will be asked to solve. Is what I'm saying.
Acha, okay, ma'am.
And you know the basic concepts of dot product, cross product, all that, right?
Yes, ma'am. I have studied
Mhm.
it in class
Uh-huh.
11th and 12th.
Yeah,
Yes, ma'am.
yeah. So you don't have to cross product, you won't be asked because that will involve all matrices and everything. But dot product is simple, so that can be asked.
Okay, ma'am. Okay.
So if you have any doubts regarding the lecture or questions, you can ask them now.
Okay, ma'am. No, ma'am. Actually, I'm not able to give enough time apart from my studies.
I understand. Sure,
Yes.
no problem. So anything else you want to discuss about any of the other lectures or anything?
Ma'am, can you please give a brief about the merging and integrating, because I have did the question wrong in assignment. Like,
Okay, so 1 second. I'll actually I don't have slides on that, but um I think all I had was 1 second. So this was all that I had actually on the slide. So this was from the previous lecture. So what sir had said is that there were 4 steps in the data processing. First, the initial images are collected. That is, so you have mounted the crystal on the goniometer and you will rotate it at different angles and get a bunch of initial images. And then the indexing is done. So each of the spots are labeled by H, K, and L. So you have collected the full set of the images, and then it is the integration of the reflection intensities. So the intensities of each of the spots are integrated, and then it is scaling, merging, and averaging of the reflection intensity data. So you have, say, 10 images from 10 different angles. So you are looking at each spot from 10 different angles. So you are getting the data about that spot in 10 different ways. So you have to merge those 10 different images to get a final 3D image. So that is what merging is. But yeah, that is like, I don't have any slides explaining that, but I can prepare some for the next lecture to make it clearer.
Okay, ma'am. Okay. Thank you.
Mhm. Okay, and anything else?
No, ma'am.
And nothing from the previous lectures and stuff also, right?
No, ma'am. No, ma'am. Am I able to ask questions after reading all these things, like in
You
next
can,
class?
I gave you my email ID in the first class, I think.
Yes, ma'am. Yes.
Or you can ask in the next class. So if you email me the questions, I will prepare the slides so that I can answer them in the next class.
Okay, ma'am. Okay.
So yeah. So I
Thank
think
you.
that's it then. Huh? Okay then. See you next class.